Alright, so today we are looking at power series, and power series is super duper cool because we're taking things and making them into polynomials, and that's the best. So first we're going to look at what is a power series, some definition-y things with interval and radius of convergence. We'll talk about why the ratio test is the best. It's because we use it all the time. That's the only reason. And then we'll look at some examples, and then we can do some stuff with power series, like adding and multiplying them, which is pretty cool. And then we're going to wrap it up with reminders of notation. So let's get started. This is the general form of a power series. What makes it a power series? Well, we have n in a power. So we're looking at our index of summation that is indexing the power on our x. And then we also have this c sub n, which is a sequence, and that also depends on our n. So as we write out our terms, because that's the thing that we do with any series, we write out terms, right? Yes? Yes. We write out terms. So as we're writing out terms, we get c sub 0 times, and then you can think about this as x to the 0 power, right? Because x to the 0 power, anything to the 0 power is 1, so that effectively goes away. And then we have c sub 1 times x to the first power plus c sub 2 times x to the second power, and so on. So this is our general form for our power series. This is a power series, and things that we can say about power series are where they're centered at, where they converge, and where they diverge. So this power series, where we're looking at just simply powers of x, and we're making a polynomial with different powers of x. It is centered at x equals 0. I should sneak this over. So centered at x equals 0. There's nothing super special about what's going on in our x right there. Sometimes the format is like x minus a or something like that, where there's a different thing that we're raising to our power, but here we just have x, so we're centered at x equals 0. And our series converges if we're looking at that looks like geometric series, right? And when do geometric series converge? When r, the absolute value of r, is between 0 and 1. So that's when absolute value of x is less than 1, and I guess that it's not 0. Right, because if it's 0, although it does converge still, right? Because if you plug in 0, then you're just going to have your value is, you're getting basically a convergence no matter what. When x is 0, it doesn't matter how many terms you're adding up, you're going to get convergence because it's just 0. And then this series diverges if you have x is greater than or equal to 1, right? Because that's when our geometric series diverges. When r is greater than 1, where the absolute value of r is greater than or equal to 1. So just to reiterate, we have a series of this form, and that's a power series centered at 0. And then I mentioned before that when we have x minus a being raised to a power, then we get a different center, because that's effectively what's making this 0, when x equals a, this part, whatever we're raising to our nth power, is going to be 0. So we're just looking for centered is wherever something that we're raising to the nth power is going to be 0. The tricky thing about power series is confusing our x and our n, because there's a lot of variables floating around now, right? Before we were only looking at sequences where the only input thing that we were thinking about was n, which was our index of summation. And that was what's going up with each term. But now we also have this x variable because we're thinking about this in terms of a polynomial. And we're constructing a polynomial. So the key, really, believe me, when I say the key to these is writing out terms. Because then you will plug things in, you will get an idea of what's happening, and then you'll be able to use all of your analysis powers to figure out what is going on. So with power series, there's 3 cases. There's 3 things that could possibly happen. You could either have that your series converges only at A, only where you're centered at, and it diverges everywhere else. where it only works at that one spot, and everywhere else, for all other numbers, it doesn't work, it diverges, your series diverges. And that's what we call a trivial case, because it only works at that one trivial spot that you're anchoring your polynomial, your power series. Another case is that your series would converge for all real numbers, so your numbers that you could plug in for x and still get a convergent power series is any value of x. So your radius, oh wait, we didn't do that yet. But you just think about all the numbers for x, you can plug in any of them and it would work. And that's lovely. That works when our power series converge for all our numbers. That's very nice. But then there's also this other case where we're looking at a particular R value, so a particular bound on where our series would change from being convergent to divergent, where our series would converge when we're looking inside this interval, but outside of that interval, our series would diverge, that we wouldn't get a number. And at those boundary points, at those values, sometimes it diverges, sometimes it converges. So just like how we were looking at optimization and we had to check our endpoints, with these, we also need to check our endpoints. Everything's coming back together. So this is what we call an interval of convergence. So the interval is how, like, what the x values are that we can have convergence versus divergence. And then our radius of convergence is going from our center, our A, to whatever that boundary point is. That's going to be our radius of convergence because it goes in both directions, kind of like a circle. Right? So we have a radius of convergence, which is like the distance. That's a really bad curly bracket. The distance is our radius of convergence, but if our interval of convergence is going to be like between our brackets, and then this is our A. So why not have 4 cases where we also never have convergence? Like, why are we allowed to say that we have convergence? We're guaranteed convergence at least at one point. Well, if you think about it, if you plug in 0, then you're going to get convergence at 0. So whatever makes this thing 0 is going to give us convergence. So that's why not never, because just try 0. And that's a classic strategy also for like making sure that things that you're setting up make sense. Just try plugging in 0, try plugging in 1, and see if you have agreement. Actually, my grandpa used to work for NASA, but he also notoriously fell asleep during lectures. So there was one time that there was a lecturer who was coming to, like, you know, teach them about something. And then my grandpa fell asleep. And then at the end of the talk, he woke up and he looked at the board and then he asked a question. And that actually, like, meant that everything that was written on the board was wrong, and the only thing that he did in his, like, just woken up from his nap stupor was that he plugged in 0 and saw that it didn't work. So, try plugging in 0, it might help a lot. So this is just another thing, I guess, of pretty much the same thing we were just talking about, where we have our power series, and we have convergence where our x values where our series converges. Those x values, that's our interval of convergence. We have like an R value. So an R value is where our series is going to converge or diverge, and R is our radius of convergence, so this distance, right, that's our R. And if our series converges only at A, x equals A, so at that one point, then we don't have a radius of convergence, so the radius is 0. And if we have convergence for all our numbers right here, then our radius of convergence is infinity. And we have a infinite interval of convergence. And this is from the book. Whoa, book. But this is a very helpful breakdown picture, right? Like, this is our kind of trivial case. This is our happy case. And this is our interval of convergence with our radius finite r radius. But see, they're all centered at A. Sometimes we like to have A as 0. That's my favorite. But there are other times that we have our centered, our power series centered at a different number. So that's why we have a general A. A is just a real number. So just looking a little bit at the notation, we have this power series, so we write out some terms, and this is centered at 0 because whatever we have in here that's being raised to the nth power, how do we make that 0? When x equals 0. For this power series, we have, it's alternating, right? Because we have this -1 to the n, so our terms are alternating, and we write out our terms because we're responsible. And this is going to be centered at x equals -1 because inside there, plug that, set that equal x plus 1 equals 0. When is that going to happen? When x equals -1. And here, this looks like we have it almost looks like we have a harmonic series, right? We have 1 over n times this other thing. So that's, it's going to be centered at when x, sorry, keep on doing x equals, x minus 1 equals 0. And when does that happen? When x equals 1. So that's why we're centered at 1. We don't have any alternating business. We just have x minus 1 because that's right in here. Plus, and then 1 over n, which is 1 over 2, times x minus 1 to the second power, and so on. So we write out some terms. Writing out 3 terms is a good start. A lot of times it's helpful to write out 4, maybe 5, because then you can kind of see more of a pattern, but 3 is a minimum start. So we are going to use the ratio test. The ratio test is beautiful because we just need to look at the next term and the previous term and use limits, infinite limits, which we can handily do because we have L'Hopital's rule. So, ratio test is what we're going to use for power series. Ratio test. What test are we using? The ratio test. All right, cool. So, what test should we use for finding our radius convergence here? You should use the ratio test? Yeah, heck yeah, we totally should. So, first we do need to figure out where we're centered at. So where are we centered at for this? We're centered at x equals 0. Okay, and then let's look at the ratio test. So our limit as n approaches infinity of our next term over our current term. So that's absolute value of our next term, n plus 1 times x to the n plus 1 over, factorial, whoops, over our current term, n factorial times x to the n. Okay, and then what do we have? Well, when we simplify that, because n plus 1 factorial is n factorial times n plus 1. So then the factorial here, I should change colors. So the factorial here cancels with this n factorial, x to the n cancels with the, cancels with the x to the n plus 1, so we're ending up with limit as n approaches infinity of absolute value n plus 1 times x. Now, when is this gonna be, like, what happens here? Well, we have infinity plus 1 times x. So no matter what x value we have, we're gonna end up with, this is gonna be an infinite limit, so this limit does not exist. And so, our radius of convergence here, our radius of convergence is 0 because we have an infinite limit there, which means that our series diverges no matter what x value we have, unless x equals 0. So, our series, our radius of convergence, our r, equals 0. Now in this example, we suddenly have a not centered at 0. When x minus 2 equals 0, when is that happening? When x equals 2. So we're centering our polynomial at x equals 2. And then we're going to try to find our radius of convergence, and that we are using the ratio test for. So we have absolute value 3 times x minus 2 to the n plus 1 power over 3 times x minus 2 to the n, it's not an n power. Okay. Well, the 3's cancel. Pew, pew. And then the x minus 2 to the n plus 1 over x minus 2 to the n. That just gives us x minus 2 in the numerator. So that means we're left with limit as n approaches infinity. Sorry, it's a bad arrow. Of absolute value x minus 2. So, are there any n's here? No, there are not. So we actually get more information here, right? Because we have x minus 2. That's our absolute value of x minus 2 is what this limit is. And so that can be a number. When does our ratio test give us convergence? When the number that we're looking at is less than 1. So if that number that we're looking at is less than 1, well, that now we have an interval of convergence and we have a radius of convergence. So our radius of convergence is 1, right? And our interval of convergence, so when we plug what x values can we plug in to this in order to satisfy this equation? Whenever x is less than 3, and then when we have oh my gosh. So yeah, when x minus 2 is less than 3, or if x is greater than negative 1. Yeah. Right. So this is our interval of convergence. We do need to check the endpoints, and that we can check with our geometric series that we end up with, so that gives us, so we don't include this, and we have 3, we also don't include this, because our geometric series that we get there, that we're raising to the n power, we need that to be less than 1. So for this, we have an alternating series. It is a power series still, and we have a 2n plus 1 factorial in the denominator. Wow, so many things. So, well, let's use the ratio test. We got limit that approaches infinity of absolute value, and then that means that all of our pluses and minuses from this part don't really matter, but we'll put them in anyway because that's responsible. So negative 1 times n plus 1 times x to the 2n plus 1 plus 1 all over 2n plus 1 plus 1. So I'm very careful that wherever I see n, I'm going to plug in an n plus 1. It's very important to do that, because otherwise you have bad algebra. And then we're going to divide that by our current term, so we're actually going to multiply by the reciprocal because we have a rational thing to work with, which is more annoying. So we have 2n, oh, sorry, that's factorial. So we have 2n plus 1 factorial in the numerator, and negative 1 to the n times x to the 2n plus 1 in the denominator. And so, what are we left with? Well, we can do some algebra. Well, that goes away with that, but it's also going to just generally go away. Up in here, this power, we're ending up with x to the 2n plus 3, because we're distributing out this 2 there. Which also means down here we have 2n plus 3 factorial. And then, so we have things that will cancel out nicely, right? We end up with 2n plus 1 times x to the second. That's another way to look at that. So pew, pew, those cancel out. 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. So pew, pew, those cancel out. And what are we left with? We're left with Sneak this over. Limit n approaches infinity of absolute value x squared over 2n plus 3 times 2n plus 2. And what happens here, as n approaches infinity, no matter what, this is going to go to 0, right? No matter what number we have for x, this is, there's n squared in the denominator and no n's in the numerator, so this is going to go to 0. So our radius of convergence is infinite. We have an infinite radius of convergence because it's always going to converge. This power series is always going to converge. It's pretty cool. So looking at this interval of convergence for this power series, what should we do? Well, maybe we should write out some terms. So we can think about this a little bit easier if we just have some terms to work with, where we have x plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4, and so on. Let's see, what would that interval of convergence look like? Let's think. Well, let's use the ratio test. Limit as n approaches infinity of absolute value of x to the n plus 1 over n plus 1 times n over x to the n. And what does this give us? Limit as n approaches infinity of, what's going to happen here? X to the n, like that. So we're left with x times n over n plus 1. Now, when is that going to give us something that is less than 1? Well, that actually depends on x, right? Because by like L'Hopital's rule, we know that this is going to end up with, that's limit as n approaches infinity of x, yep, because derivatives, okay? So then we just get x. But x is what's going to determine where our series converges or diverges. But absolute value of x is less than 1, then we know that we have convergence. And then we have absolute value of x is greater than 1, that means that we have divergence. So our interval of convergence that we're finding is from -1 to 1. But we also need to check our endpoints. So what's happening at our endpoints? If you plug in, so into here, if we plug in x equals 1 or x equals -1, we're going to have different behavior because we end up with having a harmonic series or an alternating harmonic series. So when x equals -1, we have an alternating harmonic series. So we have convergence. So we can include -1 in our interval of convergence. But when x equals +1, we have a harmonic series which diverges. So we have +1 is not included in our interval of convergence. So our interval of convergence here is going to be including -1 and not including +1. That's our interval of convergence. So let's see, what's happening here? We have an alternating series, and what is this going to end up having? X plus 1, so 1 over 1, so that's just a 1, plus negative x plus 1 over 2, plus x plus 1 squared over 4, and minus, and so on. Okay, so our interval of convergence is going to depend on our ratio test. N approaches infinity of, let's look at our next term, so -1 to the n plus 1, x plus 1 to the n plus 1, all over 2 to the n plus 1, times 2 to the n over -1 to the n times x plus 1 to the n. And what is happening? Well, pew, pew, those cancel out. Pew, pew, those cancel out. And we have limit as n approaches infinity of absolute value, so that means that all those signs go away, x plus 1 over 2. Now when is that? Oh, that doesn't depend on n anymore, does it? No, not at all. So now we can look at this x plus 1 over 2's absolute value. When that, all over 2, is less than 1, then we have convergence. But what happens at our endpoints? So our interval of convergence here is going to be, what, x plus 1 is like this, negative 2. So then negative 3 is less than, x is less than 1. So our interval of convergence is going between negative 3 and positive 1. We need to check our endpoints to see what happens there. So when x equals negative 3, that means that we end up with negative, let's write this over here. So we have x equals negative 3. That means that we end up with terms like negative 1 to the n times negative 2 to the n over 2 to the n. And what is that going to end us up with? We have positive. We only have positive values as positive 1, and this does not. When we have our geometric series, we have divergence when we have our radius is 1 or more. So we do not include negative 3. So we have our interval of convergence is from negative 3 to what? To 1. So when x equals 1, plug that in here, and what do we get? We get 2, but we also have a negative 1, and then we end up with 2 over 2 to the n, a negative 1 to the n. And so that is going to give us alternating series, but we're still having a geometric, where we still have just a 1, so we're also not including this positive 1. So our interval of convergence is from negative 3 to 1, not including our endpoints. So for our interval of convergence for this power series, and remember, power series are polynomials, so that is it's really nice in the future. So what's our interval of convergence here? Well, what is this going to actually equal? This is going to be x plus x squared over 4 plus x cubed over 9 plus other stuff. Okay, and then our limit as n approaches infinity of for our ratio test. Right, so we have x to the n plus 1 over n plus 1 squared times n squared over x to the n. We have these cancel, and we end up with limit as n approaches infinity of x times n squared over n plus 1 squared, an absolute value of this. Now what do we end up with this? Well, that limit, through our understanding of limits, we know that that's going to be the absolute value of x. So when is that going to be less than 1? Then we have convergence. If we have, so our interval of convergence is between plus and minus 1. So negative 1 to 1, but we don't know if we're including our endpoints yet, so let's plug them in. So x equals negative 1. What does that give us? That gives us our sum, n equals 1 to infinity of negative 1 to the n over n squared. So now we have an alternating series, and so this one converges. This is also a p series, and it's alternating, so that's nice. So this converges. So we also include this negative 1. And what about when x equals positive 1? what's going to happen? Well, we have not alternating, but we still have a p-series. We have 1 over n squared. So we also have convergence. So our interval of convergence is between -1 and 1, including the endpoints. Pretty cool. And so this is like alternating series. This is a reminder of p-series. This is all the things. It's great. So p-series are polynomials, so we can do things with polynomials as we always have. You can add or subtract polynomials from one another, and as long as you're on an interval of convergence that is in common between our two power series, then you're good to go. And you can do that for scalar multiples as well. It's also pretty nice. And you can also nest. You can nest power series inside each other, which is also pretty cool because you can compose polynomials and you just end up with more polynomials, right? So it still works. Polynomials work the same way that we think they have. We didn't change that. And the reason we're liking to use power series is because polynomials, remember like the first thing we did when we were taking derivatives? It was polynomials. Remember the first thing we learned to integrate with? Is polynomials. So we really like doing things with polynomials. There's nothing fancy to remember. It's just remembering the power rule. So polynomials are our friends and we like them a lot. Similarly, we can also multiply polynomials. So power series are polynomials, just written in a different way. And we can have those multiplied together and we'll be happy about that. If you want to journal about someone famous whose name comes up a lot and stuff, Cauchy is famous and stuff in math. So look into that. So the lovely thing really about power series is that we can have calculus that is easy to handle, where we are just taking derivatives of polynomials, and that's really nice. We have radius of convergence and stuff. Those are all the same. They might be different on the endpoints for our interval of convergence because of just how like the properties work out. But overall, we end up with the same radius of convergence, which is so helpful for looking at integration and derivatives. Okay, and this is just the power rule, right? Because you have the n multiplied in the front times your sequence, and then you have your x term, that's to the n minus 1, and then this is also our power rule, but in reverse for integration. So given this power series, with terms written out, it's very helpful. Can you find the interval of convergence for the integral of this, the actual function, and its derivative? So pause the video, try to work that out, and then we'll talk about that. It's easy because it's polynomials, though. So real quick, just going from here, we know that our integral is going to be c plus, and then we're going to do stuff. Shoot, okay, sorry, I forgot to record. So we have our integral, and that's going to be c plus this, which is our power rule for integration. And our derivative of this function, we're just taking our derivative of our term, which is x to the n over n. So take the derivative of that, and we're multiplying by n and raising to the n minus 1 power, and then divide by n, so you just end up with x to the n minus 1. Let's look at the interval of convergence for our integral of f. And so we have our next term over our current term, which is the same as multiplying by the reciprocal. Let's do some algebra. So those cancel. This cancels with that. And you're left with essentially x, absolute value of x is less than 1. And then we need to check our endpoints. So what's happening here? Well, if you plug in x equals plus or minus 1, what happens? Well, we get P series, and so this converges on our endpoints. P series where P equals 2, right? So we got convergence on our endpoints. So our interval of convergence is from -1 to 1, including our endpoints. Let's look at, for this one, what's happening here. We have x to the n, and so we're still going to end up with x to the n plus 1 over n plus 1 times n over x to the n. Those cancel out the same way. We end up with via L'Hopital's rule x. And so we're checking our endpoints now. If we have x, if we have this x is +1, that means that we end up with our harmonic series, and we don't like that. Well, it doesn't converge. It's not that we don't like it, it just doesn't converge. And then we have -1. When x equals -1, that means we have an alternating harmonic series, which does converge, so we include -1, but we don't include +1. And now, finally, let's look at that, our derivative, and what's going to happen here. Let's sneak over. So let's look at limit. And approaches infinity. That's a bad infinity. That's another bad infinity. X to the n divided by x to the n minus 1. And what happens here? Well, we end up with 1 less x than we wanted. So that actually ends up with for x. When is that going to converge? Converges whenever we have this x is strictly less than 1, because that's a geometric series. So we have -1 to 1, not including our endpoints. So our interval of convergence is different, but our radius of convergence for all of these, the radius of convergence is 1. It's not 2 because you're starting, you're centered at 0, and then you're going from -1 to 1, sometimes including, sometimes not, but the radius, that was a really bad curly bracket. Oh, that was really bad too. Okay, so the radius is 1, because the distance from you're centered at over to the end. So where you're centered at over to the end of your interval, that is your radius of convergence. Okay, last thing, really quick reminder, just that there are different notations that we use for higher order derivatives. Why is this useful? Because in the next section you're going to be looking at higher order derivatives as part of your series notation, so that's fun. So just remember that if you're looking at your second derivative, you got 2 little primes, third derivative is 3 primes, but then after that we switch to numbers in parentheses. And that's a pretty standard notation. This is probably what we're going to be looking at more. This is just another way of writing it, and then also engineers use other notations, so if you're reading some papers or whatever, and they're written by engineers, then they might use different notation, and that's okay. They're just kind of funny, right? But to sum up, use the ratio test because it's great, and we like doing calculus with power series because they're polynomials, and the things that we need to think about for power series are where it's centered at, what's its interval of convergence, and what's its radius of convergence. And we like to, and write out terms, write out your terms. Don't neglect to write out your terms. All right.